All right, so since there are no questions, I want to start with a nice video introducing queuing. And then we'll go into the tutorial. All right, pay attention, please. Look at this red guy. Well, that's it. Has it ever happened this to you in your life? I saw you're trying to change lines, right? Or when you drive, do you do that? Do you change lines? So, well, this is the bad strategy to do. So I will start with this, and I want you to tell me. I want you to. See, we'll talk about queuing today. So I want you to give me many examples of queues in real life, but I want you to think out of the box as much as possible, okay? I want to hear some examples of queuing to see whether this happens in real life, what we are talking today. All right, an example, please. Sorry? A passport control. That's a good one, thank you. Processes in. All right, that's also a good one. From here? Supermarket lanes, yeah. ATM queues, at the bar here, other queues. Traffic, transportation. Oh, donor transport, okay, transportation. Okay, that's also a very interesting one. Right, also. Very nice examples, actually. So yeah, you will think about POM when you go to Singapore. You have this, the customs, and then you will see how do you actually, what's going on with these waiting times over there. You'll try to calculate the waiting time till you go to get your passport done. So one nice example is inventory. The inventory, let's say at the beers that are sitting idle here, sitting at the shelf here at the bar, you can think of it as a queue. So they are being queued till you pick them up. So inventory is also an interesting thing that's related to queuing, right? Because they are waiting, and the rate of the you turn your inventory is related to what we will see today. But this is a little bit more advanced. So now we'll go into the recipe, right? So have these examples in mind. Oh my God, I don't have. Oh, well, there is no top. Okay. Oh, it's here, okay. So the recipe, and by the way, today I will tell you two expressions that if you write them in the exams, they are freebies, they will give you some more points. The lights are not on. Board light. All right. So for queuing, you have to visualize it as some customers are waiting, and here we have some servers. Let's say the servers are 2. All right? To analyze this system, there are two things to look at. We are looking at performance measures of this system. One way to look at it is on the customer side. Another way to look at it is on the firm side. Let's focus on the customer side first. What we have is the Greek letter lambda, which are the arrivals. I have it on the recipe. It's the arrival rate of customers. An example is 5 customers arriving per minute. Notice at the units of measurements. Lambda is items per unit of time. 5 customers per minute. Then we have the inter-arrivals. Inter-arrival time between first arrival, second arrival. This is also random. So I will go a little bit into UDJ now, because some people asked me, also I posted on Yammer, the Poisson, do you remember in UDJ we have this Poisson thing? Poisson with parameter lambda, right? So what does this express? What does this express? Rates. So Poisson is a discrete. Is a discrete distribution and expresses, let's say, in an interval of 5 hours, how many customers arrive at the bar, right? Maybe one here, another one here, another one here. So the number of customers, focus on that, number of customers, discrete, 1, 2, 3, 4, this follows Poisson. It's a good assumption to make with a rate lambda. It's the rate of arrivals of customers, all right? A way to a related measure of how variable the process of arrival is the coefficient of variation. Coefficient of variation is standard deviation divided by the mu. So this is the coefficient of variation of arrivals. We have a lot of random phenomena today. One random thing is the number of customers that are arriving. The number of customers, this is the CVA. So in all the examples I said before, try to find, what is my CVA here, what's going on. Because in the exams, sometimes we don't ask you in terms of customers. We may ask you in terms of patients. They go to the hospital or flights, all these examples that you gave me. We're also creative. We try to find another way to express the problem and confuse you a little bit. So coefficient of variation shows how variable a process is, and is the standard deviation divided by the mu. So for finance people, this is the reverse of the Sharpe ratio. All right? Okay, that's a good thing to remember. So this is about the arrivals. As I say on the recipe, once we see the problem is queuing, the first thing we do is we identify the parameters of the system. The most important parameter is the lambda. One is this. Then we find the CVA. If we tell you that the arrivals follow Poisson, CVA is 1 for Poisson. And I'll show you why on the recipe for Poisson. Now, for the system side, the couple of things there. First is how fast they serve these customers. Well, this is the mu. The mu. How fast, this is the rate that we serve a customer. So 5 customers per minute. We serve 5 customers per minute. And we have 3 customers per minute. So the system is in balance. Then we have, remember, from previous recipe, that mu is the rate, the service rate. Service rate. And this is related to the time. This is the mean rate that you serve, which is related to the mean time it takes to serve, which is 1 over the time. And we write it with the Greek letter tau in English. All right? Mu equals 1 over tau. The service rate is related to the time that you serve. Okay, that's the relation. So again, we have a CV, coefficient of variation of how variable the process of service times is. Notice now a related, I don't know if you did this on UDJ, for service times, I focus on this word, the time is a continuous, right? It's not discrete, it's a continuous. So the service times follow typically exponential. Sorry. parameter mu. So this expresses the variability in the time. Like one customer may take you 10 minutes to serve, another customer may take you 1 minute to serve. So this is not the number of customers, this is the times. So this is exponential. So Poisson and exponential are quite related. So, and they also, exponential also has CVS here for the service, that to be 1. So if we tell you, in 99% of the cases, you'll have CVA equals 1 and CVS equals 1. But we'll see an example today with one of them that not being 1, right? So performance measures of the system. We want to see imagine you want to improve your system. So you need to identify. You want to see how good your system performs. So one thing that we are looking at is at the average number of people in the queue. The average number of people in the queue here in this photography, let's say, of the system is 4. If you take a lot of photographs, how many people you will see waiting in the queue? This is L of Q. Length, and a way to remember it, length of the queue. Very important that we put this indicator here. Length of the queue. The mean queue length. This is 4 here. The mean length of customers, in a sense, in the system, though, is the people who are in the queue who are 4 plus 2 here, because they could be on the, being served. So this is L altogether. So L, total customers. Total customers. Sometimes we ask you about this, and you give me the L of Q. So L is the total number of customers in the system. L of Q is the number of customers in the queue, the mean number of customers in the queue. And we also have, related to that, we have the time that you spend in the queue, which is, guess what? Waiting in the queue is the average time you spend in the queue. And we also have W, which is the total time you spend in the system. So the total time you spend in the system is WQ, right, plus the time you spend to be served. The average time to be served is tau, right? That's a way to think about it. Now, there is a guy called John Little, who is actually not little at all. He's in 1961, he proved something that we call it Little's law. Little's law relates a very important W, the time you spend in the queue, with a lambda and with a L. And it's written L. You may think this is trivial, but it's not trivial at all, and has a rigorous mathematical proof behind. And it's very general. It holds for under any assumptions on the queue. Any assumptions of the arrivals of the people, they should not be Poisson. They can be anything you want. And it could be queuing network, could be anything. And this holds always. The expected number of the people in the system or in the queue, L, equals lambda, the rate of arrivals, times the time that they spend in the queue. This is the Little's law. It's small, it's little, but this is beautiful. So I want you to, I guess not many people understand what's going on here, why this is so important. I'll give you 2 little examples to remember it always. The first thing is, let's say somebody says that when it's raining, people drive slower, right? It's a fair statement. So let's say, can we see that with Little's law? So the number of cars on the road, on average, should not be affected whether it's raining or not raining, right? Let's assume that. So L is the number of cars on the road, right? The L is fixed, right? Doesn't matter whether it's raining or it's sunny. Now, the lambda, though, the rate that they are driving, when it's raining, they are driving slower. So it's lower than when it's sunny. Now, since L equals lambda times W, When this is fixed, and the rate that the cars are driving is lower, what do you think would happen to the time that you spend on the road? Will increase so that the other thing is fixed, right? So that's a way to think about Little's law, right? That's one example I want you to have in mind. Another nice example is if you want to calculate how fast you respond to emails, right? Because I said another way to think about queues is inventory. So let's assume, so in real life, you will typically have two of these things. But when you have two of them, you can calculate the third, especially related to inventory problems. So you can easily find let's say you have 240 emails on your email box. Somebody tells you that you have 240 emails. So what do you think this measure is? Your inventory, let's say, your emails you have in your email box. There are 240 emails. So this is L, as somebody said. And somehow you know that you respond to emails at a rate. No, so and you know that the arrival of, and you know that you have 60 emails, sorry. So you know that you have 60 emails per day. You are very busy. So you know that you have 60 emails per day. And you know that in your email box you have 240 emails. What does it tell you? So on average, every day you have 240 emails in your email box. And you know that you are getting on average 60 emails per day, every day, on average. What does it mean? What does it tell you on the time it takes you to respond to an email? They will be related. So if you write down Little's law, L equals lambda times W. We know this, but we don't know the time that an email is spending in the queue, actually, in our email box, till it gets out, which means we respond to the email. So if you write down W equals L over lambda, and this gives you 4 days per email. So for 1 second, that's why we need to write down the units of measurement. So L is emails divided by emails per day. So 4 days. It takes you 4 days to respond to an email, right? It's a way. If you want to evaluate companies, you may know their inventory level. You may know their rate of arrivals of, let's say, customers or buying products of this company, and then you want to know how fast you want to know the lead times, etc. So lots of questions can come up from this. All right. So that's a way to remember the Little's law and why it's so important. Now the recipe has a second page at the back, which is the second step. In the exams, we may not have one server. We may have 2 servers. So the very, very important thing in any queuing example is to find what are the servers, because sometimes the servers could be the beds in a hospital. You may think this is not a server. When you're sick, you go there. We need to find out how many beds do we need as a hospital manager. Sometimes we create examples like this in the exams. So as I say in the recipe at the back, the second step is find the number of servers. Servers we denote it by S. This is the second step. The third step is find the utilization of a server. If you have more than, so if you have one server, is lambda over mu. Rho is the utilization. Rho equals lambda over mu. Now if you have 3 servers, would be rho equals lambda divided by 3 mu, because all these servers are serving equally fast. So the capacity of the system is 3 times mu. We're assuming that the servers are equally fast. In the exams, we'll make the same assumption. In real life, this doesn't hold. It's another formula. So that's what you need for the exams. when you have S servers, it will be S times nu. Another way to express this is lambda over S times tau. Because sometimes we give you the tau, OK? It's the same thing. Now, the third, so this is the third step. The fourth step is calculate the average waiting time. Now, it's very, very important. Do we ask you the waiting time in the queue, or would we ask you the waiting time in the system? There are two cases. If you have one server, then it's very easy. It's very easy because we have a nice formula. It's good if you try to learn it by heart. So this expresses the average waiting time in the queue. The average waiting time in the queue is tau times the utilization, because you have one server, divided by 1 minus rho, times 1/2 CVA squared plus CVS squared, right? Easy? So it looks like a big sausage to swallow, but basically you learn it in the exams. The CVA and the CVS will be equal to 1. So this whole thing will cancel out, basically, right? So you'll have this. This only holds only for S equals 1. When you have S greater than 1, let's say greater or equal than 2, we will do a trick. That's why I think I have the tables at the back. We need to find WQ through Litt's law. So the way to proceed when you have two servers is we have the utilization, and we have the table that gives you, for a given utilization, it gives you the L of Q, I think, here. So tell me what's the row that you found. You find the row here, and then you find the L of Q. So knowing L of Q, you have WQ equals L of Q divided by lambda. So L of Q from the tables. All right? So when you have two or more servers, you find L of Q, the length of the people in the queue, from the tables. You have the lambda because this was in step 1. And then you find the number, the average waiting time in the system. Now, if we ask you W, we said it. W is the time you spent in the system is the time you spent in the queue plus the time you spent to be served, which is tau on average, right? Basically, that's it. That's it. And then if we ask you the length in the whole system, how many customers are in the whole system, it's the measure L, right? And L is, again, lambda times W. So if we have two servers, a way to confuse you is we have two servers, then you need to find L of Q from the tables, then you need to find WQ, then you need to find W, and then you can find the L. Is it confusing? It's good, because we want to have some, that's our job, we need to confuse you a little bit, right? So, all right, that's about the recipe. Is it crystal clear? Any questions? Yes. So when you are, very good question, you have some people waiting, and you have some servers. What's the time you spend to get served? Like, you go to the bank. What's the time you spend what's the time you spend in the bank? Is the time you spend here in the queue till you reach the first, till you find a server that is free, plus the time to be served. So the time you spend in the system, W, on average, is the average time you spend in the queue plus the time you spend to be served. Because when you go there, You may have a special request. It may take you 1 hour. Someone else may maybe do it in 1 minute. But still, you need to add this number. So be very careful what we ask you. Do we ask you about W, WQ, tau, LQ, L? We have it in the recipe, but people tend to confuse them. And let me tell you that the queuing question in the exams is the most easy one. The most easy one. And we probably will have 1 question. So we'll have 5 questions in total, 1 from processes, 1 from queuing, probably 3 from the next 2 tutorials, which is more inventory, etc. And we may have some multiple choice also. All right? So then the exercise is now try to understand, try to give you some examples about these notions. So let's go with the first one. It's a petroleum refinery. Could you please go through the first, what we say in the beginning? Yes. Need one? Okay. All right. So we have this refinery. There are some boats. You will see a very good example of this exercise when you go to Singapore, that you have all these ships waiting to enter the port. You can see it from the airplane. So you have let's see what the exercise gives us. Can somebody help me? They are telling us that it's Poisson distribution. So they are already telling us it's CVA equals 1. CVS is also 1 because we have exponential service rate. So this formula would be much easier. We will not have this side, right? Then, what else did they tell us? What's measure? What is this number 8 that they give us in terms of Greek letters? Lambda. So they give us that lambda is 8 what? 6 per week. These are the arrival rates of the ships. Then we also have, what else do they give us? You need to be fluent in Greek, right? So this is mu, me in Greek, mu. So mu is the service rate. I heard a lot of people got confused. So this is 12 ships per week. Tau is 1 over mu. Tau 1 over mu is the average time. Tau is for time. Mu is for the service rate, how fast you serve customers. All right? So we know that lambda is 8, mu is 12, and then what does the recipe say? The recipe says find the utilization, either they ask you or not. So how many servers do we have at the beginning? This is very, very important. We have 1. Lots of people confuse that, and they take wrong formulas, and the whole exercise gets messy. So we have one server, basically, and the server is this loading facility. So what's the utilization? Rho equals lambda over mu, which is 8 over 12, etc. So it's 66.6%. What does this express? Sometimes we ask you, tell me what this express, right? Quantitatively. What is this number? Is the percentage of the time that the facility is busy. On average, the facility will be busy 66% of the time. All right. Then, what's the first question? What are the average number of ships waiting to gain access? So if we draw a picture, we have one box, one server, let's say. What do they ask us now? The average number of ships waiting. So they ask us about this, which is L of Q. All right? So since it's one server, and we know exactly what they ask us, and we still have the recipe on the left hand, we go there and we say Little's law. L of Q equals lambda times WQ. Okay, we don't need Little's law because, yes, actually we need it. because we cannot find it from, let's see if we can find it from the tables at the back, because I didn't explain you the tables. Do you have the tables at the end? Sorry. So I want everyone to understand how do we use these tables at the back. All right? From the tables at the back, please have a look. The first column is utilization rate, and the other column is, the other row is number of servers. If we know that we need one server, for the given utilization we have, 66.6, we can immediately find it's something between 0.9 and 1, I think. No, 1 second. 1.20. So if you go to on the tables, you see something 1.28, and you see 1.44. Now, I will explain you how to find it exactly. But if you don't have time for the exams, just say it's something in between. That's a trick. Don't do it too often. All right? I mean, we will penalize you for doing this trick, but a little bit, not too much. If you tell me it's between these numbers, well, OK, you may lose 1 point out of 5 that has or whatever. Right? So the fastest way is this one. Right, question?
Sorry, what's the way not to lose that 1 point?
I will do it now. Let's see the fastest one. Right? The fastest, because that's the most easy question that you have in exams. Queuing is the most easy. So one way is just to go immediately. If you are lazy, you just go on the tables, you find it. And you're also smart, not just lazy. So the other way is you go through Little's law and the recipe. The recipe says we want to find this. Do we know this? We know that. Do you know that? Not yet. So we need to find it through the Kingsman formula, this big one. So WQ equals tau times rho, 1 minus rho, because the rest is 1. If CVA and CVS are equals to 1, you don't need the rest. It's much easier. It's this. Now, if we plug in, what's the tau? It's 1 over 12. What's the rho? 66.6%, 1 minus 66.6. So if you do the calculations, we'll give you 0.167 weeks. So the Little's law, L of Q equals lambda times WQ. It's good if you write it down now so that you don't study for the exams because there's no time. So you write it down now, you remember it. L equals lambda times W. It's very important. You have 6 courses, I think, right? So L of Q equals lambda times WQ. We know this, which is 8. The other one is 0.67. And this gives you 136, which are SIPs. These are the average number of SIPs waiting in the queue. Sometimes we ask you, explain me what is this number. Because are you just copying the formulas or you understand what's going on? All right? Then, yes?
So when you
multiply here?
no, WQ, CV, CVA, CVS is 1, but we also had one.
So it's 1 plus 1 divided by 2.
It's 1 by
So, all right? So when you have, again, that's a very good question. So here, if this is 1 and this is 1, and this will happen for the case that we have Poisson arrivals, exponential service times, when you see that, underline it. This and this are 1, and this simplifies. This goes away. OK? Now, all right, the second, so 1A2 says what? What is the average time a SIP must wait before beginning to deliver? What do they ask us here? Yes. It's a way to see, for me, if you are here with me. So we already have calculated that. All right? WQ, we already know that. Is it clear? Exactly. We know this already. So then the next one, 1A3. What is the average total time that the ship spends on the refinery? Sorry? That's W, which is WQ plus tau, right? It's easy one, I think. WQ, we know it. It's plus 1 over 12, and then whatever this will give us is 25 weeks. All right? Is it clear for everyone? Yes. All right, I hope so, because it's the most easy chapter that we may have today. The next one is actually more hard. All right, next question. 1B now. Now, someone, I think, is coming. OK, so the company has under consideration a second unloading berth that could be rented for $6K per week. So we write down what they give us. That rent is $6K per week. What else do they give us? That CVS is, so it's 1 again. And the service rate new is 12 sips per week. What else? The opportunity cost. We will need this later. 30K. And what is very important is, exactly, that's really, really important. As I said, actually the most, guys, if you want to say this is SOS, you know, it's the most important thing, is how many servers do we have in the system. Sometimes we add servers. And a very good question in the exams once was, we ask you to find the number of servers that we need. How many servers do we need so that the waiting time, because think about it, if you add servers, the waiting time gets lower, right? More servers you add, you lower down the waiting time for the customers. So if we ask you, how many servers should we have so that the waiting time is less than 1 day? You add servers, you start with 1 server. OK, that's a question that came to my mind. So if we ask you how many servers do you need so that, let's say, WQ is less than 5 minutes, so that your customers don't wait more than 5 minutes. How many servers would you have on average? Not on average, how many servers should you have so that your customers do not wait on average more than 5 minutes? So you start with S equals 1, and you say WQ is, let's say, 15 minutes. With S equals 2, you do all the calculations, and you find WQ is, whatever, 10 minutes. Should you increase it? Yes. You increase it, and you find WQ, let's say, 6 minutes. And hope we finish at S equals 4. So here, you do the calculation again. So this will be 4 minutes. So how many servers do you need so that the waiting time of your customers is less than 5 minutes? Is 4. That's the answer for the exams. Sometimes we ask you this. So it's a more innovative way to ask you something, right? Because we ask you the S. All right?
So there is also a trial result.
Yeah, I mean,
A trial method.
you start with the S equals 1. You increase
We
it.
need to try HS to answer the question.
Yeah.
We cannot calculate straight away.
But you don't know. You may go into 4 and you find 4. But
I forget my formula or whatever. No?
to find it through S, no, because it's non-linear. You cannot solve it through S. So I mean, that's a way to make your life a little bit harder for the exams. So apologies for that. Yeah.
First question. There are 8 ships coming per week, correct? And we can serve 12 ships per week, more than the 8.
So 8 ships, exactly, yes.
So intuitively, we cannot think that the queue will get smaller with time.
So on average, you have 8 ships, but you can serve at a rate 12 ships. So it's like you have a way to think about it is that you have, let's say, a glass, and you throw water. Water is arriving, but then some water is coming out. So the rate that the water is coming, for the rate that there should always be some water here, which is the Q. So you should always have some Q in the system.
We are entering 8 and we are retrieving 12, so the level of the water will go down.
Will go down, but this is on average. So this go up and down, but on average will be at this level. The queue sometimes may have 10 customers, may have 1 customer, may have 2 customers, but on average we'll have, let's say, L of Q people, 4. That's the idea. We are looking at expected measures here of the system, right? So, any other questions? Do you get this example I gave with the servers? I just think about it now, actually. All right, so what do they ask us here? They ask us to find, well, the question starts 1BI. But before we go, the first we will calculate is utilization, because we always need it. Utilizations is lambda over mu times S equals 8, 2 times 12. So it's 33.3% busy. So as you notice now, that the facility became less busy, right? Because we add another server, all the rest, the arrival rates there were the same. Make sense? So 2 servers have helped the system. Now, what do they ask you? They ask you, if we employ the second berth, what will be the average number of ships waiting? Exactly. Does everyone see that? We need the LQ here, the average number of ships waiting. Is it clear? All right. Now, here is the first freebie of the day. In the recipes, I think I say that when the number of servers is 2, you need the tables, but sometimes you need something that we call Thalys law. I will explain now what this is. So we need L of Q. And let's see what the tables tell us, OK? We have rho equals this. And we have S equals 2. Can you find L of Q from the tables? I don't think you can find it because it's not exactly this. It's in between, right? So I will give you a way to approximate it now. And I will give you a way to remember it and do your calculation very fast. I will call this way Thalys law. And I will explain you why. So you go on the tables. That's why we calculate the utilization. Always we calculate the utilization. So you observe on the tables. Can everyone see that on the tables? So on the tables, you have, in the end, you have rows and you have S. The S equals 2, and for rho equals 33%, you don't have it. You don't have this row. But you have rho equals 30%. And here, L of Q is what? 0.0593. Here is the one we need to find. And sorry, this is Greek. So, and then we need to find rho equals. And then we also know from the table that for 35%, we know that L of Q is what? 0.0977, OK? Now, to find that, we'll use something that's called Thalys law. Thalys. Thalys said the following. 200, I don't know when. Actually, I wrote it. He said this on the 7th century before Christ. He said, if you have, he liked queuing, right? So look at this triangle. Alpha, beta, gamma, delta, epsilon, OK? So he said the following. This over this equals to this over this. All right? So he said, alpha beta divided by alpha delta equals alpha gamma divided by alpha epsilon, OK? Now, if this doesn't sound related. I will show you why. Because we can do the same thing here. This over this is equal to this over this. And then we can find the x. Okay? It's the same thing. So this guy said it. In the exams, if you write Thalys law, it's appreciated, you know? So, so in modern times, people call this interpolation. And I will explain why. But this guy saw this already years ago. So now, we need to find this quantity by relating the other two quantities. A very simple way to remember it is 0.33 minus 0.30. So you see that? These two, you write them here. You create two fractions. On this fraction, you say these two divided by 0.35 minus 0.30. This way you cannot be confused, right? And then on the other side we have L of Q. Okay, 1 second. 1 second. 33%. So x minus 0.0593 divided by this number, 0.097, minus the other number. All right? That's the way to do this. If you read the review sheets that INSEAD gave you, they say when you're stuck, boom, there's a formula coming out of the sky. It's not this formula, it's this formula solving for x. But that's a way to remember the formula. If you are in the tables and you don't know a value, that's a way to approximate the value. You say this, you do this Thalys thing. And it's very helpful. When you write 0.33, you wrote this number. You write on the other side of the fraction, you write x. And when you write 0.30, you write the other number. So you don't need to know anything by heart. You just understand this. You don't need to have anything next to you. Just by heart, if you understand this, you will always remember it. That's the way to approximate it. And what happens, actually, that's why they call it interpolation, is that the tables give you a formula, which is something like this. And this is L of Q. And this is rho. So the tables are created by this formula. And they give you two values. They give you this value, this rho, and they give you this rho. Rho 1, rho 2. And then you find L1 and LQ and L2. But you need LQ here. You need a value in between here on the tables. So you can think that this would be in between. So what they do is they approximate with a line. And they find the value that corresponds to the line. That's what we do. All right, that's a bit too technical, but if you want to understand what's going on, is we approximate the curve with a line, and you find approximately what's going on inside. But Thalys said this 200 BC. All right? So, okay? So, back to the question. So this x is what we need. We need this L of Q. All right? So be very, very careful. How do we solve this equation? All right? Be very, very careful. If we solve it correctly, we will find 0.8023 sips. Are you getting it? All right. Good to know. So, yes, question.
In calculating the rho, we assume that the mu remains constant.
Sorry?
In calculating the rho, we assume the mu remains constant.
Exactly.
What if we have a different mu for the second verb? How do we calculate the rho?
Very, very good question. The question is, when you have two servers, what happens if one server is faster than the other one? Well, this does happen in real life. It will not happen for POM exams. All the servers are equally fast. The formula changes if they are okay, and it's a good approximation. People can say approximately they are working equally fast if it's an automated procedure. If it's very much human related, then they may have a difference rate. All right? Is it clear? Yes, question.
Why didn't we use Little's law in this case?
We will use it, I think. We will use it. We found the L of Q. So what do they ask us, actually? The average number of ships waiting. We don't need it yet. We don't need Little's law for that. So when they ask you the average number of ships waiting, you go on the tables. If you can find it from there, you do it. If you are lazy, you can say there's no time. You say approximately is a value between these two. But if you want to fully solve it, you need to calculate. And a good approximation is this one. Sorry?
It's half the first one, if you assume they work to approximate.
It's not really, I think so. Okay. So that's a way to remember it. And as I explained, is how do we find these numbers, okay? Just do this with the lines, all right? So that's about it. So then they ask you 1B2. Now we need the Little's law because they ask you W. Is it clear to everyone why they ask us a W? So W is WQ plus tau. We know the tau, but we need to find WQ. What is WQ? L of Q, LQ divided by lambda, plus tau. Is it clear? Let me explain why. Because little L of Q equals lambda times WQ. So WQ equals L of Q divided by lambda, okay? So I just plug this here. And then I think we can easily do that. This is 0, 0, 1 plus 3 weeks. This is the average time that the ship is waiting to be served in the system. Is in the queue plus the time to be served. All right? And the last question, it's related to the opportunity cost that they gave us. Is the benefit of reduced waiting time worth the rental cost of the second berth? Basically, to add a second server, it's costly. So the question is, do you need this? Is it better for you to have this second server or not? So you find the profits related to the opportunity. You want to see what has lower opportunity cost, basically. So total opportunity cost can be perceived as total opportunity cost is what? Is the time spent. What's the opportunity cost? It's the time you spend per ship for each ship in the, let's write it per ship, let's say, per ship, times opportunity cost per ship per week times average number of ships. Let's say average all right? So that's a formula for opportunity cost applied to this example. So the time spent per ship is what? So we need to compare two opportunity costs, but in the second one, you also have to add the rental cost. So cost one, I hate this. So cost one, what's the time spent per ship at the refinery? So it's WQ, actually, if I remember right. It is 0.25. Or W, no, 1 second. It's W that we need. Yes, so this is W. This is a cost, and this is opportunity cost, and this is average number of ships, L. So what's the cost of the first system? Is 0.25 times, opportunity cost is the same, is 30K times 8 SIPs. No, it's here, this is the new average number, 1 second. So this is the rate of the SIP, 1 second. So opportunity cost in the system is the time spent per SIP times, so this should be lambda here. Average number of SIPs arriving so this is lambda. All right? This is the 8. That's the first one. The second one, what's the opportunity cost of the second system that we have? Is 0.093 times 30K times 8 plus rental cost. And here we can, if you do the calculations, you can find it around 28K. And here you can find it roughly 60K dollars. All right. And we have a total estimated gain of 31K, whatever. Because this has lower, with the second berth, we have less costs, so it's worth a consideration. Basically, that's the exercise. It's a simple exercise, basically, but a bit confusing in the end. All right? 6K. It's given somewhere at the beginning of the exercise. All right? So I promise you 2 freebies. The second freebie is variability is evil, right? Now it's very funny because sometimes people think they will get extra points. So I remember a guy was writing this in every single question. Variability is evil. He could not finish the exam, so he was writing this. And in one question he didn't write it. So I said, okay, it's interesting. But he said, in the end, please note, variability is evil. All right? So sometimes people are funny in the exams. So the second exercise now is related to voting, right? So you write it one time in the exam, once or maybe twice. Because if you write 10 times, it will give you 10 points. Okay. So please go through the question. Please go through the question. Here, it's very similar. It's very similar, but we have one measure, CVS, I think, is greater than 1. And let's see what's going on. And it's a way for you to refresh if you understand all the concepts very easily. And then if you understand everything, you don't need to study anything about queuing. You basically got it. That's about it. All right, voting. So can somebody help me? And please tell me what measures do they give us? Because the first thing in the recipe is tell me what are the inputs. What is this 35? First of all, how many servers do we have here? Is it clear to everyone how many servers we have? So we have S equals 1 server. Very good thing. Because sometimes it's very important to understand what are the servers. And that's why I press you to tell me some examples of queuing to understand, I want you to think out of the box. When you have a car, the server is the traffic light, for example. It doesn't have to be a person over there, right? So you are waiting, and someone is about to serve you. So he's the server. So here the server is 1, and is the box that you are voting, I think, is the place that you can vote. And they give you the average service time is it's 100 seconds. So, okay, if you want to transform seconds into minutes, it's 100 seconds over 60 minutes. So this will be 1.67 minutes. What's the tau? Can somebody explain me what tau is? The time. Average time to vote. It's very important to understand what the Greek letters are. So tau is time. Average time to serve. Arrival rate, again in minutes, is 35 seconds divided by 60. So it's 0.583 voters. Okay, this doesn't make much sense, but theoretically it does. 0.583 voters per minute arriving at this voting facility. And what else do we know? Utilization. Rho equals lambda times tau. That's another way to write the utilization. Because you can find the mu, but that's another way to do it. Lambda times, because in the exams, you want to do things very, very fast. Lambda times tau, 0.583 times 1.67, right? And this will give you 97% busy. Notice that if this is above 1%, don't write in the exams. Utilization is 300%, you know? Something's wrong here. Just don't write it. Just say something's wrong. Should be less than 1. I mean, or you write it and you cross it, something's wrong here, you know? Okay, so that's utilization. And then we have, what else do they tell us? CVA equals 1. And then they don't give us the CVS, but they express it. So CVS is sigma over mu. What's sigma? 120 divided by 100. And this gives you 1.2. As I posted on Yammer, why we have this CVS is because if somebody gives you the variability, this is an absolute measure. Here, this is a relative measure to the mean. That's why it's important. Because if somebody tells you the waiting time at the bar, let's say, is 5 minutes on average, but if you don't know if this is a lot. But if somebody, because if you are waiting for a surgery and this takes you on average 1 minute, is it a lot or not? You need to compare it with the mean to have an indicator of how variable the process is, right? That's why we divide by the mean, and then this is a unitless quantity. So here, back to the exercise, they ask you how long on average a voter have to wait in line before entering in a booth. So what do they ask you? What measure do they ask you? If you are confused, just draw something like this, and then how many servers do we have? 1. All right. What do they ask us here? So first of all, the keyword is time. Time means W, wait. And then, is it in the queue or is it in the system? These are the things. So they ask you about WQ. Now, can we find it? It's tau. You need to learn it by heart. Tau times rho, 1 minus rho, times 1/2, CVA square, plus CVS squared. If you miss that, you miss everything. So this is not 1. This is 1.2. And we know everything else, OK? Is it clear for everyone that we know everything? Because I wrote it here, right? OK, so if we put this on the calculator, it's 65.9 minutes. And this is the average time that a voter would have to wait to cast his vote. 65.9 minutes, OK? Is it clear? Yes, please.
I thought tau was 1 over mu.
Exactly.
But over there, we just put mu in minutes.
So 100 seconds. Suppose that it's water.
So the time spent on average is, that's the mu, isn't it? 100 seconds. So tau should be 1 over 100?
But it says 100 seconds in the voting booth. In parentheses, this is the time needed to cast his vote. So when they tell you time is tau, time you spend to be served. Mu is rate. So this is time, tau is minutes per voter. Per voter. That's why the units of measure are quite important. But the mu, I want you to remember always mu is items per time. Whereas tau is time per item. An item could be customer, could be anything, all right? And remember that these are average times, because these things are random. Yes?
Will we be allowed to have formulas at exam?
It's, yeah, of course it's allowed. We have this, you can have the recipes. You can have the recipes and your favorite book with you. All right? So, it's open book exams, right? It's open books. So, okay, before we relax too much, let's go to the next question. Let's go to the next question. Please bear with me. 310, okay? Next question, can you please go through it? We're almost there. So, we do what? One solution is we add 3 additional voting machines. So this is the key word. We underline it. Exactly. So here the S is for, so everybody gets that? Because we say we add 3, in the exams you don't have time, people think S is 3. So they get confused, some people. I say again, this is the easiest questions we may ask you. It will be one big question. We try to make it as less confusing as possible because we want you to get it. But that's the easiest one. Sorry? The harder question will be next time. But some people will go to Barcelona next time, which is on Saturday. Right? I think. So that's why we have everything at the beginning of the P2. So the servers here are 4. What do they ask you? What measure do they ask you? Is it clear? Some people already said it. What do they ask you here? WQ, right? WQ. So you have 4 servers. What does the recipe say? You need Thalys, etc. That's why I put it there, so that we see another example of Thalys. All right. So WQ equals L of Q divided by lambda. Okay? So what do we know here? We know tau equals 1.67. We know lambda is 0.583. And we know that rho is what? Lambda divided by S times tau, which is 24% here.
Why tau you don't change tau?
Yes, the tau didn't change. You can add more servers, but if they are working equally fast, for each server, the tau is the same. That's an assumption that people are working equally fast. The servers are serving equally fast. So the rho here will go down, it's 24%. Previously it was 97%, wow. Because we added 4 servers. Yes? The time? Exactly, yes, I'm really sorry about that. Good catch, thank you. So it's lambda over mu, exactly, yes. Sorry about that. So So here we need the WQ. Again, from the tables, you can find L of Q. We go on the tables to find L of Q. But we go to the tables, we see that for this utilization rate, you don't have it. So you write again, for rho equals 20%, what's the L of Q from the tables? And then for rho equals 30, sorry, this L of Q is what? 0. Does it make sense? If the rho is low, the length, so let's see of these numbers, right? Why the length of the Q is larger when the utilization is larger? It's more busy system, right? So the length of the Q is higher, right? Does it make sense? Now, how do we find this number? Thalys, exactly. So this divided by this equals this divided by this. Let's do it together. All right. Please help me. 24%. Yeah, you can say like 24 times minus 20 divided by 30 minus 20. And then equals, so 24, what is here? Is LQ. Is it clear? 20, it's this one. And then for 30 is this one, 0.0159, okay? So that's how we construct it. Thalys, okay? Thalys law. Okay, L of Q is, if you do the calculations, so that's what the review sheets gives you. The review sheets says apply a formula that there's no way to explain it, which is like this. Minus, I'm writing down so that people don't ask me, where does it come from? And then times so in the review sheets, you have 4 review sheets. They say L of Q is this formula, but there's no way for me to explain you how this comes from, right? If you want to approximate, that's a way to remember it, I think, with this Thalys law thing, all right? So if you do whatever you want, if you solve this equation, or if you do this equation here, you will find L of Q to be 0.0078 what? Voters. If you understand the units of measurements, you understand what we are calculating. All right? Approximately. Yes?
Sigma is 75 seconds here, so can we rearrange it's not Poisson distribution?
Exactly.
So can we use the data?
Very, very good question. Very good question. That's why I said approximately. I will come back to this. The tables gives you, assume that it's Poisson arrivals and exponential service times. Here, it's not. When it's not, we can still use the tables, but approximately. All right? It will not hold exactly the same. Approximately, it's a very, very good question. Approximately, the tables hold. So here, we can still use it, but we say approximately. OK? So L of Q is this one now. Remember, they asked us something else. They asked us about WQ. WQ is LQ divided by lambda, and then 0. Divided by 8, no, 0.583. 583. So this is exactly minutes. That's it. That's the number it will take you to cast your vote. The same, you need to do this calculation when you go to Singapore, so that you find the time, to get your passport done, right? But trust me, you may start doing it over there, or in the US. So that's about it. That's about it. So please, if there are any questions, right? We finished 10 minutes earlier. If there are any questions related to the course, a very good point actually is that at some point, the professor will mention that you need to submit the innovation exercise. Have you thought about it? So innovation exercise, I think, gives you 10, 20% of the total grade. So what is this? Is you need to write a clean startup idea in one page. I think they ask you to find, okay, tell me your idea. Tell me if anyone has done it. It's no problem, maybe someone has done it already. I think it's not your startup idea. It's actually a business model innovation something that you think is business model innovation, basically. So you need to tell us why this is business model innovation. Are there any competitors over there? What is interesting over there? And this will give you 10, 20% of your final grade. Don't spend too much time about it, right? It does count, but don't spend too much time, right? But this will come back after some point. Next time, we'll talk about inventory. Inventory, it's very important. If you go to Barcelona, enjoy. Thank you. Question?
I have a question.
Yeah.